Something is deeply wrong with the comet that isn't acting like a comet. China's Mars orbiter just sent back images that defy every model we thought we understood. Three-eyed Atlas should have been ripping itself apart after losing over 13% of its mass in its dive past the sun. It should have had a blazing tail, a roaring stream of dust and ice stretching hundreds of thousands of kilometers behind it. Instead, it's just a blurred sphere of light, no tail, no debris, no signature of violent outgassing. Silence where physics says there should be chaos. And that's only anomaly number 1. There are now 10 documented behaviors that break every pattern we've recorded from thousands of comets. Individually, each is rare. All 10 together, the statistical probability drops below 1 in 10,000. No one is calling it artificial, but everyone is saying the same thing. Whatever just passed through our solar system is not behaving like anything we've ever seen. October 3, 2025. While most of Earth wasn't paying attention, China's Tianwen-1 probe locked onto a faint moving spark from Mars orbit. The spacecraft had been looping around the red planet for more than 4 years, its main mission long completed. But this was different. This was humanity's closest look at an interstellar visitor. The object was hurtling through the inner solar system at 58 kilometers per second, roughly 129,000 miles per hour. At that speed, you could orbit Earth in 18 minutes. Three-eyed Atlas itself was small, only 5.6 kilometers wide, barely the width of Manhattan. And yet, it was 18 million miles from Tianwen's camera. Now imagine that challenge. A high-resolution camera built to photograph Mars from low orbit suddenly had to track something. Smaller than a city, darker than asphalt, moving faster than anything naturally bound to our sun, nearly 30 million kilometers away. China didn't announce they were attempting the observation until they succeeded. And on November 5th, they released the frames, stark black and white images of a hazy sphere wrapped in a diffuse cloud. The coma stretched thousands of kilometers wide. Officially, they called it a major technical accomplishment and a rehearsal for future deep space missions. But here's what they didn't highlight, the part that matters. These are the closest, clearest images humanity will ever get of Three-eyed Atlas. Closer than Hubble, closer than James Webb, closer than any Earth-based telescope could ever dream of being. Yes, the European Space Agency's Mars Express and Trace Gas Orbiter also observed the encounter, but Tianwen-1 captured the sharpest data. And that data revealed something quietly staggering. Or rather, it revealed the absence of something fundamental. When a comet races near the sun, it superheats. Volatiles trapped in primordial ice erupt outward. Solar wind blasts this material into the classic glowing tail, dramatic, violent, unmistakable. But Three-eyed Atlas didn't do that. It didn't even try. And that's when astrophysicists realized this object is breaking rules that have held for billions of years. Three-eyed Atlas passed perihelion on October 30th at 0.9 astronomical units from the Sun. That's closer than Earth, closer than Venus at certain points in its orbit. NASA's Jet Propulsion Laboratory detected something remarkable in the trajectory data: non-gravitational acceleration. The comet was being pushed by its own outgassing with measurable force. The numbers are specific. 1 astronomical unit from the Sun, Three-eyed Atlas experienced a radial acceleration of 1.1 times 10 to the negative 6 astronomical units per day squared, pushing it directly away from the Sun. It also showed a transverse acceleration of 3.7 times 10 to the negative 7 astronomical units per day squared, perpendicular to the Sun's direction. Using momentum conservation, the math tells us something definitive. To produce that level of acceleration, Three-eyed Atlas must have lost at least 13% of its total mass during the perihelion passage. 13%? That's not a gentle evaporation. That's violent outgassing. For a comet massing 30 billion tons, we're talking about 4 billion tons of material ejected into space in a matter of days. 4 billion tons of gas and dust should create a spectacular display, a massive coma, a prominent tail, streaming debris visible for millions of kilometers. This is basic physics. This is what happens to every comet that passes this close to the sun. So where is it? On November 5th, two separate observatories captured post-perihelion images of 3I Atlas. The Virtual Telescope project in Italy and the R. Navis Observatory in Spain both released their photographs on the same day. Both showed the same thing: a compact fuzzy sphere, a small coma, no obvious tail. The sun's direction in these images is clearly marked. Anti-sun is clearly defined. That's where the tail should be, pushed by solar radiation pressure and the solar wind. That's where 4 billion tons of ejected material should be streaming away from the nucleus. It's not there. Compare this to Comet Lemon, a regular solar system comet. The same RN Navis Observatory photographed Lemon just 2 days earlier, on November 3rd. The difference is stark. Lemon has a clear, well-defined tail pointing precisely away from the sun, exactly as expected. It looks like what a comet should look like. 3I does not. Now, before we go further, let's address what this might mean. There are conventional explanations being discussed. Maybe the material ejected during perihelion was primarily gas, not dust, making it harder to see. Maybe the viewing geometry is wrong and we're looking at the tail edge on. Maybe the mass loss calculations are incorrect and less material was actually ejected than the non-gravitational acceleration suggests. These are reasonable hypotheses. They're being investigated. But here's the thing. Each explanation requires its own set of special circumstances. And when you start stacking special circumstances on top of each other, when you need multiple unlikely things to all be true simultaneously, that's when scientists start paying very close attention. Because 3I isn't just anomalous in this one way. The missing tail is the 10th documented irregularity. There are 9 others, each independently strange, each requiring its own explanation. Let's go through them. Not to sensationalize, but to understand exactly what we're dealing with. Because whether this object is natural or not, it represents something we've never encountered before. And the pattern emerging from the data is at minimum deeply unusual. Anomaly 1. The trajectory. When 3I Atlas was first detected on July 1st, astronomers immediately began calculating its orbit. Within weeks, something became clear. The comet's path through our solar system is aligned with the ecliptic plane to within 5 degrees. That might not sound significant, so let me explain what it means. The ecliptic plane is the flat disk where all the planets orbit. Earth, Mars, Jupiter, they all circle the sun in roughly the same plane, like marbles rolling around the rim of a dinner plate. This makes sense because they all formed from the same spinning disk of dust and gas 4.6 billion years ago. But 3I Atlas didn't form here. It came from interstellar space, where there is no preferred direction, no cosmic flat plane that all stars follow. Interstellar objects should arrive from random directions, from any angle relative to our solar system's orientation. Up, down, sideways, diagonal. There's no reason for them to align with our planetary disk, and yet this one does. Its trajectory is retrograde, meaning it orbits opposite to the planets. But it does so almost precisely within the same plane. The probability of this happening by chance, 0.2%, 1 in 500. That's the first anomaly. Before we even get to its composition or behavior, its arrival path is already statistically unusual. Anomaly 2, the sunward jet. During July and August of 2025, multiple observatories captured something unprecedented. 3I Atlas was shooting a jet of material toward the sun, not away from it, toward it. This isn't supposed to happen. Comets develop tails that point away from the sun because solar radiation pressure and the solar wind physically push the ejected gas and dust outward. It's like trying to blow smoke into a fan. Physics simply doesn't allow material to stream sunward against that pressure. Now, there is a phenomenon called an antitail, an optical illusion, where the viewing geometry makes a comet appear to have a spike pointing toward the sun, but it's not real. It's just our perspective seeing a curved tail edge on. Astronomers know how to identify these illusions. They've seen them hundreds of times. The sunward jet from 3I Atlas wasn't an illusion. Multiple teams analyzed the geometry, they checked the viewing angles, they ran the calculations. This was actual material being ejected toward the sun, defying the radiation pressure that should have pushed it the other way. No conventional comet has ever displayed this behavior. No natural mechanism adequately explains it. Anomaly 3, the mass and speed combination. Remember, 3I Atlas has a nucleus about 5 to 6 kilometers wide with a mass estimated at 30 billion tons. That's 1,000,000 times more massive than Oumuamua, the first interstellar object discovered in 2017. It's 1,000 times more massive than Boros, the second interstellar comet found in 2019. Now add the speed. 3I Atlas is moving faster through the solar system than both of those previous visitors. Not slightly faster, significantly faster. Here's why this matters. In interstellar space, larger objects are statistically rarer than smaller ones. It's basic physics. There's more small debris than large rocks. Fast-moving objects are also rarer than slow ones, because ejecting something at high velocity requires more energy. The probability of detecting an interstellar object that is both exceptionally large and exceptionally fast, according to the statistical models, less than 0.1%, 1 in 1,000. We've now seen 3 interstellar objects. The third one happens to be 1,000 times more massive and moving faster than the others. That's not impossible, but it's deeply improbable. Anomaly 4, the arrival timing and planetary encounters. 3I Atlas didn't just pass through our solar system. It passed close to multiple planets with precise timing. In September, it flew within tens of millions of kilometers of Mars. The European Space Agency's orbiters were in perfect position to observe it. Then it swung past Venus. Then its trajectory brought it near Jupiter. Each encounter was close enough for detailed observation, but not so close as to significantly alter the comet's path. Each happened when spacecraft were present and operational. And here's the interesting part. The arrival time was fine-tuned, so that at perihelion, when the comet was closest to the sun and potentially at its brightest, it was completely unobservable from Earth. The sun was directly between us and the comet, making ground-based observation impossible. It's as if someone planned a tour of the solar system's major observation platforms while avoiding direct visibility from the planet with the most telescopes. The probability of this timing occurring naturally, 0.005%, 5 in 100,000. Anomaly 5, the chemical composition. When spectroscopic analysis of the comet's coma began, something strange appeared immediately. Nickel, lots of nickel. More nickel than iron, which is extremely unusual. In typical comets, if metals are present at all, iron dominates. The ratio of nickel to iron is well established across thousands of observations. But 3 Atlas flips this ratio. It has more nickel than iron, a pattern seen in industrially produced nickel alloys, not in natural cosmic ice balls. Even more striking, the ratio of nickel to cyanide is orders of magnitude higher than any known comet, including Boris, the previous interstellar comet. Orders of magnitude means factors of 10, 100, possibly 1,000. This isn't a slight variation, this is a completely different chemical signature. The probability of a natural comet displaying this composition? Below 1%. Anomaly 6, the missing water. Comets are supposed to be dirty snowballs. Water ice is their primary component, often making up 70 to 80% of the total mass. When they approach the sun, that ice vaporizes, creating the distinctive coma and tail we associate with comets. 3 Atlas contains only 4% water by mass. 4%. That's not a comet, that's barely ice at all. It's more like a rock with a slight frost coating. This contradicts everything we know about comet formation. Whether in our solar system or any other, comets form in the cold outer regions where water ice is abundant. There's no known formation mechanism that produces comet-sized objects with such low water content. And yet, 3 Atlas is classified as a comet because it does show some outgassing. It's active. It's just not active in the way comets should be active. Anomaly 7, extreme negative polarization. This one gets technical, but stay with me because it's crucial. When light reflects off a surface, it becomes polarized, meaning the light waves align in specific directions. The degree and type of polarization tells us about the surface properties, the size and shape of particles, the composition. Every comet ever observed, including the interstellar comet Boris, shows a consistent polarization signature. Scientists have built models based on thousands of measurements. The patterns are predictable. 3 Atlas shows extreme negative polarization, unprecedented in the entire database of comet observations. Not slightly different, completely off the charts. The light reflecting from its surface is polarized in a way that doesn't match any natural dust grain models. The probability of this occurring in a natural comet, below 1%. Anomaly 8, the WOW signal alignment. In 1977, a radio telescope detected a powerful narrowband signal from space. It lasted 72 seconds, was far stronger than background noise, and appeared to come from the direction of the constellation Sagittarius. The astronomer reviewing the data was so surprised he circled it and wrote "Wow" in the margin. The signal never repeated. Its origin remains unexplained. 3I Atlas arrived from a direction in the sky that coincides with the WOW signal, to within 9 degrees. 9 degrees is a relatively small patch of sky, about 18 times the width of the full moon. Is this meaningful? Maybe not. The WOW signal's exact source location was never precisely determined, and 9 degrees is still a fairly large area. But the probability of random coincidence? 0.6%. Anomaly 9, the unprecedented brightness surge in color. Near perihelion, 3I Atlas brightened faster than any comet in the observational database. Not just faster, dramatically faster. The rate of brightening didn't match any existing models of cometary outgassing. Additionally, during this brightening phase, the comet appeared bluer than the sun. Normal comets reflect sunlight, so they appear roughly the same color as the sun, maybe slightly redder due to dust. Blue comets are extraordinarily rare because there's no common mechanism that selectively scatters blue light more than red light in typical dust grains. Whatever was causing 3I Atlas to brighten was also causing it to emit or reflect an unusual spectrum. Blue, bright, and fast-changing, all at the same time. And now, Anomaly 10, the missing tail despite massive mass loss. Which brings us back to where we started. The non-gravitational acceleration proves substantial mass loss. The physics is clear, the math is straightforward. 4 billion tons of material left that comet's surface in a matter of days. Where did it go? If it formed a typical dust tail, we would see it. If it formed a gas tail, spectroscopic observations would detect it. If it fragmented into larger chunks, tracking systems would have spotted those fragments. Instead, we see a compact coma and no clear tail, as if the ejected mass simply vanished. Now, let's be absolutely clear about something. Each of these anomalies, taken individually, has potential conventional explanations. Maybe the trajectory alignment is just luck. Maybe the sunward jet was a short-lived rotational effect. Maybe the composition reflects an unusual formation environment in another star system. Maybe the missing tail is an observational limitation. But here's where it gets uncomfortable. These aren't individual anomalies. They're 10 simultaneous anomalies in the same object. And when you multiply probabilities, when you ask, what are the chances that all 10 of these unlikely things happen together in the same comet, the numbers become very small. Less than 1 in 10,000, possibly less than 1 in 100,000, depending on which statistical models you use. This is what Harvard astrophysicist Avi Loeb has been emphasizing in his recent analyses. Loeb is known for unconventional hypotheses.
He suggested Oumuamua might be artificial. Many colleagues disagreed, but his methodology is sound. When something displays multiple independent anomalies, each unlikely on its own, you cannot ignore the pattern. Loeb isn't claiming 3i Atlas is a spacecraft. He's not saying it's alien technology. He's saying the data doesn't fit natural phenomenon.
Comet models, and that's worth investigating seriously. He's calling for more observations, more analysis, more attention to the details that don't add up. And he's not alone anymore. The observation data is public. Other researchers are now running their own analyses. Some agree with Lowe's interpretations, some don't. But everyone agrees the object is unusual. So what are we actually looking at here? What are the possibilities? The conventional explanation remains the most likely. 3A Atlas is a natural comet from another star system formed under conditions different from anything in our solar system, displaying behaviors we haven't seen before simply because we've never observed an object quite like this. Maybe it formed around a star with a different chemical composition, explaining the unusual nickel to iron ratio. Maybe its parent system had different temperatures and pressures in the comet-forming regions, explaining the low water content. Maybe we're simply seeing natural phenomena pushed to their statistical extremes, all happening to coincide in one object. This is the position most scientists hold, and it's not unreasonable. The universe is vast. Statistical outliers must exist. We've only observed 3 interstellar objects. Our sample size is tiny. It would be premature to conclude anything extraordinary based on limited data. But there's another possibility, one that's harder to discuss in scientific circles without being dismissed, but one that the data keeps suggesting we consider. What if 3A Atlas is not entirely natural? Not a spacecraft necessarily, not a probe in the way science fiction imagines, but something designed, something directed, something that serves a purpose beyond random wandering through the cosmos. Think about the trajectory again. It entered our solar system aligned with the ecliptic plane, passed near Mars when multiple spacecraft were present, swung past Venus, came close to Jupiter, all while remaining hidden from Earth-based observation at perihelion. That's either an extraordinary coincidence or an intentional route. Think about the composition. More nickel than iron, orders of magnitude more nickel relative to cyanide than any natural comet. Nickel alloys are what we use in spacecraft construction because of their strength and heat resistance. Is that meaningful? Maybe not, but it's worth noting. Think about the missing water. 4% water content makes this object more like an asteroid than a comet. Asteroids are denser, harder, more durable. If you wanted to send something on an interstellar journey lasting millions of years, would you build it from fragile ice that evaporates or from rock and metal that endures? Think about the sunward jet, material ejecting toward the sun against radiation pressure, with no clear mechanism to explain it. Unless the mechanism isn't outgassing, unless it's something else, something active. Think about the non-gravitational acceleration without a visible tail. The comet is being pushed by something. We can measure the force, but we can't see what's creating that force. 4 billion tons of material is missing, but there's no debris field. Where did it go? Now, I'm not saying any of this proves artificial origin. I'm saying the pattern is strange enough that we shouldn't dismiss the question out of hand. Science advances by asking uncomfortable questions, by entertaining hypotheses that seem unlikely until the data forces us to take them seriously. Avi has been receiving criticism for his willingness to discuss these possibilities. Some colleagues say he's being sensationalist, that he's damaging his reputation by suggesting interstellar objects might be anything other than natural. But Lowe's response is simple. The data is what the data is. If 10 independent anomalies appear in the same object, that's not sensationalism, that's observation. And recently, something interesting happened. Lowe received an email from Chile from an electrical engineer named Dario Villin. Villin wrote to thank him, not for being right or wrong about 3i Atlas, but for making the topic accessible, for inspiring people who never thought they'd care about astrophysics to suddenly pay attention. Villin mentioned his 18-year-old daughter who had been unsure about her career path. She's now considering astrophysics because Lowe's analyses of 3i Atlas made the field seem alive, uncertain, full of genuine mysteries rather than settled facts. That's what's valuable about moments like this. Not the answer to whether 3i Atlas is natural or artificial, but the reminder that we don't have all the answers. The universe still surprises us. There are still objects we can't fully explain, and that's exciting. Right now, 3i Atlas is moving away from the Sun at over 200,000 kilometers an hour. By December 19th, it will pass about 270 million kilometers from Earth, roughly 700 times the distance from Earth to the Moon. For a few days, the most powerful telescopes will have one last chance to observe it in detail. After that, it's gone. By January 2026, 3i Atlas will exit the solar system completely. It will return to interstellar space, traveling at speeds that will carry it light years away within decades. We will never see it again. No future generation will get another look. This was our one opportunity. The data we've collected will be analyzed for years. New papers will be published. New interpretations will emerge. Some scientists will argue the anomalies are explicable through conventional means. Others will continue to question whether we're missing something fundamental about what this object really is. But there's a deeper question here, one that goes beyond 3i Atlas specifically. It's about how we approach the unknown. For most of human history, we assumed Earth was the center of everything. Then we learned we orbit the Sun, not the other way around. We assumed our Sun was unique. Then we found billions of other stars. We assumed planets were rare. Then we found thousands of exoplanets. We assumed interstellar objects were theoretical curiosities. Then we detected 3 in 8 years. Every time we've assumed the universe works one way, we've been forced to expand our thinking. And every time, the expansion has been humbling. So when an object arrives from another star system displaying 10 separate anomalies, each individually unlikely, all present simultaneously, what should our response be? Should we force it into existing models because that's intellectually comfortable? Or should we acknowledge that maybe, just maybe, the universe has shown us something we don't yet have the framework to understand? I'm not advocating for belief in alien artifacts. I'm advocating for intellectual honesty. The data from 3i Atlas is strange. That's not opinion, that's measurement. Multiple independent research teams have confirmed the anomalies. The numbers are public. Anyone can verify them. What we do with that strange is, how we interpret it, that's where the debate begins. And it's a healthy debate. Science isn't about consensus. It's about evidence, analysis, and the willingness to revise our understanding when the data demands it. Here's what we know for certain. 3 Atlas is the most massive interstellar object ever detected. It's moving faster than its predecessors. It has a chemical composition unlike any known comet. Its trajectory through the solar system followed an improbably convenient path for observation. It displayed a sunward jet that defies conventional physics. It lost at least 13% of its mass at perihelion, but shows no corresponding tail. Here's what we don't know. Why? We don't know why any of these things are true. We have hypotheses, some more conventional than others, but we don't have definitive answers. And that's okay. That's where science lives, in the space between observation and understanding. That's where discovery happens. The TN1 images released on November 5th will be studied for years. Those blurry black and white frames, captured from Mars' orbit at a distance of 18 million miles, represent the closest look humanity will ever get at this object. Future researchers will enhance them, analyze them, compare them to other datasets, searching for details we missed on the first pass. Maybe those details will resolve the anomalies. Maybe they'll deepen the mystery. Either way, they matter, because 3 Atlas is not the last interstellar object we'll detect. It's the third of many. As our detection systems improve, as our telescopes become more sensitive, we'll spot more of these visitors passing through our cosmic neighborhood. Each one will teach us something. Each one will challenge our assumptions in different ways. And eventually, maybe in our lifetimes, maybe in the lifetimes of the next generation of astronomers, we'll understand what these objects really represent. Are they cosmic flotsam? Random debris ejected from other star systems by gravitational interactions, wandering the galaxy without purpose or direction? Or are they something else? Something intentional? Messages in bottles cast into the interstellar ocean?
waiting for someone to notice? We don't know yet. But here's what makes this moment in history remarkable. We're finally in a position to ask the question seriously. We have the technology to detect these objects. We have the instruments to analyze them. We have the mathematical tools to calculate probabilities and assess anomalies. For the first time in human history, we can do more than speculate about whether we're alone in the universe. We can gather data, we can make measurements, we can test hypotheses. 3 Atlas may not provide the definitive answer. It may remain ambiguous, a fascinating puzzle rather than a clear revelation. But it's moved the conversation forward. It's shown us that interstellar objects are more complex, more varied, more surprising than we anticipated. And it's reminded us that the universe doesn't owe us easy answers. It doesn't organize itself according to our expectations. It simply is what it is. And our job is to observe, to measure, to question, and to follow the evidence wherever it leads. Even if that leads to uncomfortable places. Even if it challenges our assumptions about what's possible. Even if it forces us to consider explanations we'd prefer not to entertain. Because that's what science is. Not the
collection of established facts, but the process of confronting the unknown with intellectual courage. The willingness to say, I don't know, when the data is ambiguous, and the determination to keep investigating until clarity emerges. 3i Atlas has given us that opportunity. It's shown us something genuinely strange, something that doesn't fit neatly into existing categories. Whether that strangeness ultimately points to exotic natural processes or something more profound, we can't say yet. But we can say this: we witnessed something extraordinary. We documented it, we measured it, we preserved the data. And now we have to sit with that uncertainty, that productive discomfort of not knowing until better data or better theories provide illumination. That's where we are in November 2025. Watching an anomalous object depart our solar system, carrying with it more questions than answers, reminding us that the cosmos is far stranger and more wondrous than our models suggest. The object is still visible through large telescopes, still moving at 129,000 miles per hour, still racing back toward the interstellar void from which it came. We have weeks, maybe months of observation time remaining. Some teams are still collecting data, still running analyses, still trying to extract every possible piece of information before it vanishes forever. What they find may not resolve the debate. It may just add more questions to the pile. But that's okay. Questions are valuable. They drive us forward. They keep us honest. They prevent us from becoming complacent about our understanding of reality. And here's the truth that makes this moment so significant. We're living through the beginning of interstellar object astronomy. Not the middle, not the mature phase, the beginning. Think about where we were just 8 years ago. Before Oumuamua, interstellar objects were theoretical. We knew they had to exist, ejected from other star systems drifting through the galaxy. But we'd never seen one. We had no data, no measurements, no understanding of what they actually looked like or how they behaved. Now we have three data points where once we had 0, and each one has been radically different from what we expected. Oumuamua accelerated without visible outgassing, tumbled in a way that didn't match any known object, and disappeared before we could study it properly. Boris looked more conventional, a comet that actually behaved like a comet, but even it had unusual carbon monoxide concentrations. And now 3i Atlas with its 10 documented anomalies and its fuzzy images from Mars orbit. 3 objects, 3 mysteries, and we're only getting started. The next generation of telescopes will be more sensitive. The Vera Rubin Observatory, scheduled to begin operation soon, will scan the entire visible sky every few nights. It will detect fainter objects, more distant objects, objects moving at angles that current surveys miss. Conservative estimates suggest we might detect 1 interstellar object per year once Rubin is fully operational. Optimistic estimates put the number higher. That means within a decade, we might have 10 or 20 interstellar objects in our catalog. Within 2 decades, hundreds. Each one a visitor from another star system, each one carrying information about conditions we can't study any other way. Because here's what's remarkable about interstellar objects: they're free samples from alien worlds. Not alien in the sense of biology or intelligence necessarily, but alien in the literal sense, foreign, from elsewhere, formed under different conditions, shaped by different processes, composed of materials that might not exist in our solar system. Every interstellar object is a messenger. It traveled for millions or billions of years to reach us, carrying with it the chemical signature of its birthplace, the physical scars of its journey, the story of a star system we'll never visit. And for a brief moment, as it passes through our neighborhood, we have the chance to read that story. 3I Atlas is one chapter, a strange, confusing, provocative chapter that raises more questions than it answers. But it's not the final chapter. It's barely even the introduction. The data we collect now will inform our understanding of future visitors. The anomalies we document will become the basis for new theories. The questions we ask today will shape the research programs of tomorrow. And eventually, as the sample size grows, patterns will emerge. Maybe we'll find that objects like 3I Atlas are common, that the first three we detected were actually unrepresentative outliers. Maybe we'll find the opposite, that most interstellar visitors are mundane rocks and ice balls, making 3I Atlas even more extraordinary by comparison. We don't know yet, but we will. That's the promise of this new field of astronomy. We're not stuck speculating about what might be out there, we're observing what actually is out there, documenting it, measuring it, arguing about what it means. And sometimes, just sometimes, the data will surprise us. It will show us something we didn't predict, something our models can't easily explain, something that forces us to expand our understanding of what's possible. 3I Atlas is that kind of surprise. Whether it turns out to be an exotic natural phenomenon or something more, it's pushed the boundaries of our knowledge. It's made us reconsider assumptions we didn't even know we were making. It's reminded us that the universe is under no obligation to make sense on our terms. There's a humility in that realization, a recognition that we're still novices, still learning the basic vocabulary of cosmic phenomena, still building the frameworks we'll need to truly understand what we're seeing. But there's also excitement, because if the universe can surprise us this thoroughly with just 3 interstellar objects, imagine what we'll learn from the next 100. Imagine the discoveries waiting in the next decade, the next generation, the next century. Right now, somewhere in interstellar space, another object is on its way to our solar system. Maybe it's already inside the orbit of Neptune, undetected because it's too faint or moving at the wrong angle. Maybe it won't arrive for another 10 years, or 50, or 1,000. But it's coming. They're all coming. The galaxy is full of these wanderers, and some tiny fraction of them pass through our cosmic neighborhood. Each arrival is an opportunity, a chance to learn something new, a chance to test our theories against reality, a chance to be surprised. And maybe, just maybe, one of these objects will be so unusual, so thoroughly anomalous, that it forces us to confront a question we've been dancing around for decades. Are we alone? That's the subtext running through every discussion of 3I Atlas, every analysis of its chemical composition, every calculation of its trajectory probabilities, every debate about the missing tail. The question we're all thinking, but most are hesitant to voice: could this be evidence of something beyond natural processes? Could 10 simultaneous anomalies, each individually unlikely, be a signal rather than noise? I'm not saying it is. I'm saying we should be intellectually prepared for the possibility that someday one of these interstellar visitors might genuinely be artificial. A probe, a messenger, a piece of abandoned technology, something constructed with purpose rather than assembled by random collisions and gravitational interactions. That day might not come in our lifetimes. It might never come at all. The universe might be full of natural wonders and empty of artificial ones, and that would be a valid answer to the question of whether we're alone. But if that day does come, if we do detect something genuinely artificial passing through our solar system, the first step will be recognizing it. And that recognition will come from asking the right questions, from developing the analytical tools to distinguish artificial from natural, from being willing to consider explanations that seem outlandish until the data makes them necessary. 3 Atlas might not be that object, probably isn't, but it's teaching us how to look, how to analyze, how to think about interstellar visitors as more than just astronomical curiosities. It's training us for whatever comes next, because something will come next. Another object, another mystery, another data set that challenges our understanding, and then another, and another. This is the new normal in astronomy. Interstellar objects are no longer theoretical. They're observable, measurable, analyzable phenomena that we'll encounter regularly for the rest of human civilization. Our children will grow up in a world where interstellar visitors are routine astronomical events. They'll read about 3 Atlas in textbooks, see the 10 Win-1 images in museums, learn about the 10 anomalies that sparked so much debate in 2025. And maybe by then, we'll have answers. Maybe the mystery will be resolved, the anomalies explained, the debate settled. Or maybe not. Maybe 3 Atlas will remain a puzzle, an unsolved riddle from the early days of interstellar object astronomy. The strange comet that broke all the rules and vanished before we could fully understand it. Either way, it matters. It matters that we documented it. It matters that we ask the difficult questions. It matters that we preserve the data for future analysis, because science is cumulative. Every observation builds on previous observations. Every mystery that remains unsolved today becomes a clue for researchers decades from now, working with better instruments and more complete theories. The 10 Win-1 images, those blurry black and white frames of a fuzzy sphere without a tail, will be studied by scientists who haven't been born yet. They'll enhance the images with algorithms we can't imagine. They'll compare them to databases of hundreds of interstellar objects. They'll see patterns we're currently blind to. And maybe they'll understand what we witnessed in October and November of 2025. Maybe they'll explain why 3 Atlas behaved the way it did, why it displayed so many anomalies, why 4 billion tons of ejected material left no visible trace. Until then, we sit with the uncertainty. We continue analyzing the data we have. We prepare for the next interstellar visitor, and we remember that the universe is vast, ancient, and strange beyond our current capacity to understand. 3-eyed Atlas came from somewhere, a star system perhaps hundreds of light-years away, orbiting a sun we'll never see, formed from materials and conditions we can only infer. It traveled for millions of years through the void, through temperatures near absolute zero, through radiation fields and gravitational wells, carrying with it the chemical signature of its origin. And then, for a few brief months in 2025, it passed through our solar system. It came close to Mars, close to Venus, close to Jupiter. It approached the Sun at 9/10 of an astronomical unit. It experienced extreme heating, violent outgassing, forces that would have destroyed most comets. It lost 13% of its mass in a matter of days. And then it left, accelerated by forces we measured but couldn't see, racing back toward interstellar space at speeds that will carry it light-years away within our lifetimes. We got one look, one opportunity. China's Tianwen-1 captured the closest images we'll ever have. Ground-based telescopes documented its post-perihelion state. Spectroscopes analyzed its composition. Mathematicians calculated its trajectory and acceleration. And now it's over. 3-eyed Atlas is leaving. By the time you hear this, it might already be beyond the orbit of Mars, moving outward, dimming, becoming harder to observe with each passing day. In January 2026, it will cross the boundary of our solar system and return to interstellar space. It will continue its journey through the galaxy, perhaps for another 1,000,000 years, perhaps for 1 billion, until some gravitational interaction alters its path or some catastrophic collision ends its existence. But the data remains. The images, the measurements, the spectroscopic analyses, the trajectory calculations, all of it preserved. All of it available for future researchers to study, to question, to reinterpret in light of new discoveries. That's what we do as scientists. We document the universe as best we can. We make measurements. We preserve data. We ask questions. We admit when we don't have answers, and we keep looking, keep observing, keep trying to understand. Three-eyed Atlas reminded us of something we tend to forget. The universe still has teeth. It still throws curveballs, still shatters our predictions, still laughs at the neat little models we build on our tiny blue world. 8 years into the study of interstellar visitors, and we're still standing at the shoreline of a cosmic ocean we barely understand. We're still getting blindsided, still facing phenomena that don't fit into any category we've invented. And honestly, that's exactly where science belongs, at the ragged edge of the known, uncomfortable, curious, hungry. Because the opposite, a universe without surprises, where everything behaves exactly as expected, would be a smaller universe, a duller one, a cosmos without magic. Three-eyed Atlas didn't give us comfort. It gave us something infinitely better: questions. Real, testable, unsettling scientific questions that will fuel entire fields of research for years. Questions that poke holes in our assumptions. Questions that remind us how much of reality remains untouched, unseen, unimagined. As the comet fades from our telescopes, slipping back into the interstellar dark, it leaves us with those questions. 10 documented anomalies, 1 impossible visitor, and the quiet certainty that it wasn't the last. Even now, another object is drifting between the stars, already on its way, already carrying its own riddles. We just haven't noticed it yet. But we will. We have the telescopes, we have the instruments, we have the relentless curiosity that keeps humanity pointed upward, generation after generation. And when that next traveler arrives, we'll be here, collecting data, breaking models, asking the hard questions, preserving the evidence for minds not yet born. That's the true promise of this new era in astronomy. Not perfect answers, but discovery. Not certainty, but wonder. Not the death of mystery, but the beginning of understanding. Three-eyed Atlas was strange, unprecedented, counterintuitive, and utterly, undeniably real. We witnessed something extraordinary. We recorded it, and now we move forward, eyes open, instruments ready, waiting for whatever comes next. Because for the first time in history, we're no longer alone in our corner of space. We can see beyond the walls of our solar system. We can study matter forged in other suns, shaped by alien environments, traveling unimaginable distances. And some of these visitors will be strange. They'll violate expectations. They'll challenge physics. They'll expand our imagination. That's not a warning. It's an invitation. So here's to Three-eyed Atlas, the visitor from another star, the comet that behaved like nothing we've ever seen, the object that shed 13% of its mass yet grew no tail, the anomaly that ignited global debate and will shape research for decades. We will never see it again, but we will never forget it. And somewhere out there, in the silent gulf between suns, another traveler is already on its way. We'll be watching.